Welcome to the Deep Dive. We're here to help you cut through the noise and really get to grips with the essential stuff. Today, we're diving into a key part of our CSWIP 3.1 exam prep series. In welding inspection precision, deep knowledge, understanding the details, it's not just nice to have, it's absolutely paramount. Our mission today, to navigate some, pretty critical concepts every aspiring welding inspector really needs to master. We'll look at core principles, specific scenarios, and break down those crucial insights you need to excel.
Exactly. And this isn't just about listing facts for you. We want to illuminate why these things matter. We'll connect it all back to real-world welding quality, structural integrity, and fundamentally, safety. Understanding these nuances, that's what really makes the difference between just knowing things and being truly well-informed and effective on the job.
Okay, great. Let's unpack this with our first scenario then. When we're talking about, qualifying a new weld procedure, there's a very specific sequence. Quality control depends on it. Before any test welding actually happens for qualification, what's that absolute first document, that first procedure that gets prepared? Is it a WPS? Or maybe a WPQR, a WPR, or something called a PWPS?
That fundamental first step, the one that really kicks everything off, that would indeed be the PWPS.
PWPS.
Yeah, the preliminary welding procedure specification. Think of it as the initial blueprint, your first draft, if you like. It outlines all the proposed parameters of the process, filler materials, joint design, preheat, all those essential variables. And crucially, this is before any test welding or formal qualification. Its role is absolutely foundational. It guides that very first test weld, sets the stage for what you plan to achieve. It's the starting point. Everything else gets evaluated against it.
Okay, so preliminary is the key word there. Does that imply it's like a hypothesis you're testing, or is it already pretty set in stone?
It's definitely more like a structured hypothesis. It's based on existing knowledge or maybe calculations predicting how it should work, but it's not yet proven for that specific application.
And thinking about you, the inspector listening, what's maybe a big red flag you'd look for in that PWPS? Something that screams potential problem even before metal is joined.
Good question. A major red flag would be vagueness. If it lacks specific details on essential variables, that's trouble. Or conversely, if it proposes parameters that are just way outside industry norms or what the chosen process or materials can realistically handle. The real insight here isn't just knowing PWPS comes first. It's seeing that a well-crafted, realistic PWPS is your first defense against, costly failures and requalification headaches. It's not just paperwork, it's a predictive tool. Helps you see potential success or failure early on.
That's a great perspective. Visualizing success or failure from the start. Okay, let's move on. Let's talk about something absolutely fundamental. Heat. Controlling heat. Welding involves intense heat, obviously, and managing that energy input is critical for a sound weld. But what do we actually mean by high heat input in welding? Let's look at some numbers you might see. Would high heat input be, say, 550 joules per millimeter, 55 joules per millimeter, maybe 5.5 joules per millimeter? Or is it 5 kilojoules per millimeter?
Right. When we're talking high heat input, the answer there is 5 kilojoules per millimeter, 5 kilojoules per millimeter.
Okay.
And this is a really good point for clarity, especially with units. That kilo prefix is easy to miss. 5 kilojoules is actually 5,000 joules per millimeter.
Oh, okay. Big difference.
Exactly. Compare that to 550 millimeters or the other options, and you see why 5 kilomillimeters stands out as significantly high. And the implications of putting that much heat in, they're profound. It can lead to excessive grain growth, both in the weld metal itself and in the heat-affected zone, the HAZ. And that often means reduced toughness. The weld becomes more brittle, more prone to cracking. Plus, high heat input tends to increase distortion, can cause real headaches with fit-up and leave behind harmful residual stresses.
So it's clearly not just about melting metal. It's about controlling the thermal cycle very precisely. If there's one core insight an inspector should really take away about heat input, what would you say it is?
Yeah, I'd say the critical insight is this. Heat input is like the material's memory keeper. Every joule you put in or fail to manage correctly leaves an irreversible mark on its microstructure. Its properties change. So an inspector isn't just checking a number on a procedure. They're decoding the material's history, its current state, and predicting its future strength, all through that one metric. The really experienced inspector knows it's a balancing act, finding that optimal range, not just avoiding being way too hot or way too cold. That's where the expertise lies. Thermal precision, really.
Thermal precision, I like that. Okay, let's shift gears slightly. Let's talk about preventing problems. Specifically, cracking, probably one of the most feared defects. Now, different welding processes, because of how they work, can be more prone to certain types of defects. So think about submerged arc welding, SAW, compared to manual metal arc MMA or stick welding. What kind of cracking is associated more often with SAW than with MMA? Are we talking hydrogen cracking in the HAZ, solidification cracking in the weld metal, maybe reheat cracking during post-weld heat treatment, or lamellar tearing?
The one most specifically associated with SAW, more so than MMA in this context, is solidification cracking in the weld metal.
Solidification cracking.
Okay, yeah, sometimes called hot cracking. It happens right as the weld metal is freezing, solidifying. It's mainly a concern in processes that create a large, deep weld pool, and SAW definitely fits that bill. The larger weld pool in SAW, plus its typically slower cooling rate compared to MMA, means the metal stays molten for longer.
Right.
And that gives more time for impurities, things like sulfur and phosphorus, to segregate, to gather in the last bits of liquid metal to freeze. These impurities can form weak films at the grain boundaries, which then crack open under the shrinkage stresses as the weld cools down.
Makes sense.
MMA, on the other hand, usually has smaller, faster cooling weld pools, so it's generally less susceptible to the specific type of cracking. Now, hydrogen cracking can happen in both, sure, but it's often more strongly linked with MMA, especially with certain electrode types if preheat isn't right. Reheat cracking is a PWHT issue, and lamellar tearing relates more to the parent material quality itself. So for SAW versus MMA, solidification cracking is the key difference here.
That's really clear. The large pool, slow cooling in SAW really sets the stage for it. I've heard stories, about just a tiny bit too much sulfur turning a potentially strong SAW weld into a problem. How does knowing these process-specific tendencies really sharpen your focus as an inspector out in the field?
Oh, it sharpens it immensely. It allows you to be predictive. If you know you're inspecting a critical SAW weld, you'll automatically be more vigilant for signs of solidification cracking because you understand that inherent risk profile. I remember a project quite early in my career, actually, heavy plate, lots of SAW, bro. We kept seeing these tiny micro cracks in destructive tests. The first thought was maybe hydrogen. But knowing SAW's characteristics, that deep pool, we pushed to check for solidification issues.
Yeah.
And sure enough, material analysis showed sulfur levels were just creeping up at the high end of acceptable, enough to cause trouble with that specific procedure. That was a real aha moment for me. It drove home that this process-specific knowledge isn't just academic, it's a powerful diagnostic tool. It helps you target your inspection efforts where they're needed most, helps prevent costly rework or much worse.
Yeah, being proactive rather than just reactive. Makes perfect sense. Okay, let's switch to materials. How clever material choices can head off serious problems. Think about certain types of stainless steel specifically. Low carbon austenitic grades, and also stabilized stainless steels. When we deliberately choose these materials for a job, what major risk are we primarily trying to minimize? Is it HAZ cracking? Is it something called weld decay? Weld metal cracking? Or maybe distortion?
With those specific types of stainless steel, the low carbon or the stabilized grades, the primary target we're aiming to prevent is weld decay.
Weld decay. Okay, what exactly is that?
Weld decay is a specific form of intergranular corrosion. It attacks the grain boundaries. It happens when stainless steel is heated into a particular temperature range, roughly 450 to 850 degrees Celsius, like during welding and held there, or cools slowly through it. What happens is chromium carbides precipitate. They form right at the grain boundaries. This formation actually depletes the chromium from the area immediately around the grain boundary.
Ah, so it steals the chromium locally.
Precisely. And it's the chromium that gives stainless steel its corrosion resistance. So those depleted zones along the grain boundaries become very vulnerable to corrosive attack. Now, using low carbon grades, the L grades like 304L or 316L simply reduces the amount of carbon available to form those harmful carbides in the first place. Less carbon, less problems.
Simple enough.
And the stabilized grades, they contain elements like titanium or niobium. These have an even stronger affinity for carbon than chromium does. So they preferentially react with the carbon, forming stable titanium or niobium carbides, effectively tying up the carbon. This stops the carbon migrating to the grain boundaries and reacting with chromium. So it prevents that chromium depletion, protecting against weld decay.
That's fascinating. It's like a chemical preemptive strike within the steel itself.
Yeah.
From your perspective as an inspector, how does really understanding this material science empower you? Does it go beyond just checking the material test cert?
Oh, absolutely. It empowers you to be more of a detective, not just a checker. You're not just confirming what material grade was used, but
Yeah.
understanding why that specific grade was necessary for that service environment. The real insight is recognizing that this battle against weld decay is happening at the microscopic, even atomic level, and material selection is a key strategy. So as an inspector, knowing this helps you anticipate vulnerabilities. What if the wrong grade was accidentally used? Or what if welding parameters, like maybe the interpass temperature, weren't controlled properly, potentially sensitizing even the right material? It deepens your ability to assess true compliance and predict long-term performance, especially in demanding corrosive environments.
That deeper understanding makes a huge difference. Okay, one last scenario. Let's talk about a crucial preparation step, preheating, especially for thick sections. You imagine this. You're using MMA, stick welding, to join a pretty thick 60-millimeter wall nozzle to an even thicker 100-millimeter wall vessel shell. Heavy stuff, high stakes. To make sure the preheat is done correctly, when and where should that temperature be thoroughly checked? Should it be checked before welding starts and also before any restarts? Should it be checked on both the shell and the nozzle? Or should it be checked at points at least 75 millimeters away from the joint edge?
Right. For a critical, heavy section joint like that, the comprehensive and correct answer is all of the above.
All of them. Okay.
Absolutely. This is absolutely not a place to cut corners. Each one of those checks is vital for the preheat to be effective. Let's break it down. First, checking before welding starts and restarts. That ensures the minimum required preheat temperature is actually achieved before you strike an arc, and critically, that it's maintained throughout. If welding stops for a break, the metal cools. You must bring it back up to temperature before restarting.
Makes sense. Maintain the heat.
Second, checking on both the shell and the nozzle. This is vital because you've got two components, maybe with different thicknesses, different thermal masses. They need to be heated uniformly. Uneven heating causes differential expansion and contraction, which can induce serious stresses.
Got it. Uniformity across the joint.
And third, checking at points at least 75 millimeters from the joint edge. Why that distance? Because it ensures you're measuring the bulk material temperature, the heat soak, not just a superficial surface heat that might dissipate quickly. That 75 millimeter gives you confidence you've heated a sufficient volume of material around the joint to the required temperature. That's what's needed to slow the cooling rate effectively and prevent problems like hydrogen cracking or excessive hardness.
So it's about heating a significant zone, not just the immediate edge. This really brings up an important point. Why is such a rigorous, multifaceted check absolutely critical, especially in heavy fabrication like this vessel scenario? What are the real-world consequences if an inspector misses something or if it's not done properly?
The consequences, honestly, they can be catastrophic, especially with thick sections. If preheat is insufficient or not maintained or not checked properly, you're basically setting the stage for potential failure. Rapid cooling in these thick sections leads to hard, brittle microstructures in the HAZ, and crucially, it traps any hydrogen that might be present. That combination significantly increases the risk of delayed hydrogen cracking. Cracks that might not even appear immediately, but days, even weeks later.
Weeks later. Wow.
Yes. I've seen situations where hydrogen cracks discovered long after welding compromised entire structures. Huge costs for repairs, sometimes complete replacement. And think about it, in a thick-walled pressure vessel, these aren't just minor flaws, they are potential catastrophic failure points. The safety implications are immense. Loss of containment, potential loss of life. For you as an inspector, this is where that meticulous attention to detail, verifying every aspect of the preheat procedure, truly saves lives and prevents disasters. It's that important.
Absolutely critical. That really drives home the responsibility involved. So we've covered quite a bit today. From the foundational PWPS, the impact of heat input, understanding specific defect risks like solidification cracking and unsobu, using material science against weld decay, and the comprehensive checks needed for preheating thick sections. Each of these details, as we've seen, is really a cornerstone of quality welding inspection essential knowledge for your CSWIP 3.1 studies and your career.
And maybe connecting it all to the bigger picture, just remember, none of these elements exist in a vacuum. They're all interconnected. The final quality of that weld is a sum of many, many parts. From that initial PWPS, setting the plan, to careful heat management, controlling the microstructure, selecting the right material for the job, executing precise preheat. Every decision, every check you make directly impacts the structural integrity, the performance, the safety, the longevity of whatever is being built. The real deep dive insight maybe is that you're not just inspecting isolated pasts, you're helping orchestrate the overall quality, ensuring all these steps work together to create a safe, reliable result. It's a holistic view.
A holistic view. That's a great way to put it. Building that complete understanding. Keep exploring these topics. Keep asking questions. Keep building that robust knowledge base. Your dedication to getting these details right is what makes an exceptional inspector. We look forward to our next deep dive with you.